Assalamualaikum warahmatullahi wabarakatuh.
A very good morning to all of you ladies and gentlemen, and welcome to the International Conference on Science and Applied Science, ICSAS 2022.
It is an honor for us to welcome all of you to Solo and this conference. On behalf of the organizing committee, I am Suci Faniandari and my partner,
Iqbal.
We are from Physics Department Graduate Program Universitas Sebelas Maret. Would like to extend our gratitude and great appreciation for your presence here.
So ladies and gentlemen, on this beautiful occasion today, please allow me to greet this conference, also the invited speaker of ICSAS 2022. We can give a round of applause, ladies and gentlemen, to the Honorable Professor Ahmad Yunus as Vice Rector for Academic and Student Affairs. Good morning, Prof.
Dr. Harjana as Dean of Faculty of Mathematics and Natural Sciences, Universitas Sebelas Maret. Good morning, Doctor.
Professor Fenty Suryanti as Vice Dean for Academic Research and also Student Affairs.
Dr. Desi Suci Handayani as Vice Dean for Human Resource, Finance and Logistic Affairs.
Dr. Fahru Nur Rashid as Vice Dean for Planning, Partnership, Business and also Information Affairs.
Professor Chari as the Head of Physics Doctoral Program, Universitas Sebelas Maret.
Professor Budi Purnama as the Head of Physics Master Program, Universitas Sebelas Maret.
And Professor Agus Supriyanto as Head of Physics Undergraduate Program, Universitas Sebelas Maret. And to the Honorable our keynote speakers, Professor Moh Khoirul bin Ahmad from University Tun Hussein on Malaysia. Good morning, Prof.
Professor Muhammad Aziz from the University of Tokyo, Japan.
Associate Professor Mohsen Farahat from Central Metallurgical Research and Development Institute, Cairo, Egypt.
And also Associate Professor Henry Widyandari from Universitas Sebelas Maret, Indonesia.
We also take this opportunity to welcome our invited speaker, Professor Thomas Jamaluddin from National Research on Innovation Agency of Indonesia, and Prof. Thomas will present his research in parallel room number 3.
Also here, a warm greeting to our moderator previous today conference, Dr. Ubaidillah and also Dr. Engineering Kusumandari.
We kindly also enjoy this conference as we are going to have a great discussion in this ICSAS 2022, which is organized by Physics Department, Graduate Program, Faculty of Mathematics and Natural Sciences, Universitas Sebelas Maret.
So ladies and gentlemen, here talking about the aim of ICSAS 2022 here to bring together scholar, also leading researcher and expert from diverse backgrounds and application areas in sciences here. A special emphasis is placed on promoting interaction between here the scientists, theoretical, experimental, and also educational science and also engineering today.
So that a high-level exchange in new emerging areas within mathematics, chemistry, physics, biology, applied mathematics, and all areas in science is achieved. That's why we are so happy to welcome all of you to this discussion at ICSAS 2022, and we hope this conference to be fruitful and engaging to all of you.
So ladies and gentlemen, in this great occasion, to start this meeting, I would like to ask you, all rise here. So we are going to sing our national anthem, Indonesia Raya, led by our previous conductor. Ladies and gentlemen, please rise. Ladies and gentlemen, please be seated.
Ladies and gentlemen, to begin this agenda, I would like to give a chance for the committee chair to deliver his speech. I kindly please Professor Budi Purnama, as chairman of ICSAS 2022, to come on stage to deliver his speech. Ladies and gentlemen, please give round of applause to Professor Budi Purnama.
Assalamualaikum warahmatullahi wabarakatuh. Honorable Vice Rector of for Academic and Student Affairs, Professor Ahmad Yunus. Honorable Dean of Faculty Maths and Natural Sciences, Dr. Arjana. Honorable Keynote Speaker of ICSAS 222, Professor Herul, Professor Aziz, Professor Mohsin, and Professor Hendry. Honorable Invited Speaker of ICSAS 222, Professor Thomas Jamaluddin, and all presenter ICSAS 222 and colleagues from Physics Department, Sebelas Maret University. First of all, we would like to express our gratitude to Allah Subhanahu wa Ta'ala, who has given us healthy and opportunity that we can meet in ICSAS 222 seminar, either to face on site or through online media Zoom meeting. Second, on behalf of the organizing committee, we are honored and delighted to welcome you to the International Conference on Science and Applied Science 222. This conference was the seventh conference which was organized by the Physics Department, Sebelas Maret University. On this occasion, the ICSAS 222 was held hybrid conference. This conference is aimed to bring together scholars, leading researchers, and experts from the diverse between the theoretical, experimental, and other topic-related physics. In this ICSAS 222, there are 8 parallel sessions and 4 keynote speakers, including 1 invited keynote speaker. The keynote speaker is follow. The first, Professor Muhammad Aziz from Department of Mechanical and Biofunctional System, Tokyo University, Japan. Second, Professor Muhammad Khairul bin Ahmad from University Tunisia on Malaysia. Third, Professor Mohsen Farahat from Central Metallurgical Research and Development Institute, Egypt. And the fourth, Professor Henry Witiandari from Physics Department, Universitas Sebelas Maret, Surakarta. Well, the conference participant, there is 101 participants which were submitted abstract via the submission conference system. Then the 61 papers will be presented to its parallel session in ICSAS 222. And then for the final decision, the paper will publish in Scopus Index Proceeding, AIP. We deeply thank the author for their enthusiastic and high-grade contribution. The ICSAS 222 would not be possible without the dedicated effort of many people who have worked with us in planning and organizing the program. We are grateful to the volunteers who contributed to the various processes that make up the conference, and it would not be possible for me to mention one by one in this submission. Finally, I hope that during this conference, you find the conference fulfilling and enjoyable. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Budi Purnama, for the warm welcoming speech.
So, ladies and gentlemen, we are also pleased to invite the Vice Rector of Academic and Student Affairs, Universitas Sebelas Maret, Professor Ahmad Yunus, to give an opening speech and to open the conference officially. Ladies and gentlemen, please give a round of applause to Professor Ahmad Yunus. Time is yours, Prof.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. The distinguished Dean Faculty of Mathematics and Natural Science, Bapak Dr. Harjana, and also Vice Dean 1, Professor Fenty Suryanti, Vice Dean 2, Bapak Dr. Sahrul, and Vice Dean 3, Ibu Dr. Desi, the honorable invited speaker who willing coming to Solo, Professor Dr. Muhammad Khairul bin Ahmad from University Tunusan Un, Malaysia. Thank you, Prof. Khairul, to participate in our international conference. And also, keynote speaker, Professor Muhammad Aziz from Department of Mechanical and Biofunctional System, Tokyo University, Japan. Associate Professor Muhsin M. Farahat from Central Metallurgical Research and Development Institute from Egypt. And Associate Professor Henry Widyandari from Department Physics, Universitas Maret, Surakarta. And also the Honorable, the Head of Study Program of Physics, Professor Agus Suryanto. On behalf of the organizing committee and also the leader of University Sebelas Maret, at this precious moment, let us first express our gratitude to merciful God who has granted us blessing and grace that we could gather here today to attend the 7th International Conference on Science and Applied Science 2022, which this year held in the Department of Physics, Sebelas Maret University. Let me extend my warm greeting and welcome to our distinguished speaker and participant. Ladies and gentlemen, this conference is very important to us to improve our scientific research collaboration, and this activity will improve our level in World University ranking distinguished. This conference is one special event for researcher and lecturer to enhance the atmosphere academic, especially in international research collaboration after this conference. It is an occasion for positive contribution, idea, and knowledge sharing regarding the development of future science and applied science in UNS and also in Indonesia. Finally, I hope all participants of this conference can find important areas of common ground in the best way for achieving the broad goals. I have great pleasure in formally declaring this convention with say Bismillahirrahmanirrahim, the International Conference on Science and Applied Science 2022 is open. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Ahmad Yunus, for opening ICSAS 2022 officially.
Ladies and gentlemen, next on schedule, we will have a photo session. We will invite to come forward Professor Ahmad Yunus,
Dr. Harjana,
Dr. Fahrun Roshid,
Professor Khairul,
Associate Professor Henry Widyandari,
Dr. Ubaidillah,
Dr. Engineering Kusumandari,
Professor Chari,
Professor Budi Purnama,
and also here Professor Agus Suprianto. Please to come forward.
Okay, before our speakers present their materials, I would like to mention uh, the resume or background or biography for TS Doctor Professor. TS means IR or engineer. Okay, TS Dr. Muhammad Hairul bin Ahmad is professor in Department of Electronic Engineering, Faculty of Electrical and Electronics Engineering, and he is also principal researcher of microelectronics and nanotechnology, Sweden Research Center, or MINT SRC, at University Tun Hussein on Malaysia. Professor T.S. Dr. Muhammad Khairul's research focus on nanostructures, oxide materials such as TiO2, titanium oxide, and also zinc oxide. Uh, Professor Khairul also interested in dye-synthesized solar cell, oxide material-based thermoelectric wastewater treatment, and mechanoluminescence. Prof. Khairul received his first degree from Guma University, Japan, in 2003, where he studied electronics engineering in 2009, and he continued his master degree at University Technology Mara, UITM Shah Alam. And then he received his doctoral engineering from Shizuoka University. Okay, the second keynote speaker will be mentioned later. So I invite Prof. Khairul to give his speech. Without any further ado, 30 minutes is yours. Thank you very much.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good morning. Thank you, Mr. Chairman. Respected Prof. Ahmad Yunus, Vice Chancellor Academics and Student, I think. Dr. Hajana in of Fakultas MIPA. Respected researchers and docent. Okay. Firstly, I would like to thank the organizer of ICSAS 2020 for invited me as a keynote speaker. This is my second time come to Solo, but my first time to visit the campus of UNS. I found it very I think in Japanese they call it suzushi, means nyaman, nyaman sekali, because of so many trees in the campus. Okay, different with my campus in UTHM. We have a large scale of areas in UTHM, but not as many as trees in UNS. So I would like to suggest my chancellor, vice chancellor, to plant many trees like UNS. Okay. Okay. Today I would like to share my students and my research. Thank you for the introduction just now, Mr. Chairman. my research area is about based on nanostructured material. That nanostructured material that I want to usually my interest is in dye-stacked solar cells and water treatment, and then we will use also for wastewater treatment. So today I would like to share the useful of nanostructured material and use it in wastewater treatment. The title of my speech today is Enhancing Photocatalysis of Electron Trapping in AG Dope Flower Light Rotar-phase TiO2 film by hydrothermal method. Okay, so if you look at the title, it's about photocatalytic. Photocatalytic. Usually TiO2 is famous in photocatalytic due to the some drawback of TiO2. So conventional TiO2. So we prepare in nanostructured and we enhance it with nanostructured. Okay. Okay. Before that, there is I prepared some introduction of my university. Okay. Next is some introduction of my university background. Okay. Is our university started from 2000, I think 1990. Okay, we started as a polytechnic campus. At that time, our university is to train polytechnics researchers and researchers and lecturers. So after that, we upgraded to ITO Institute, and then we upgraded to College University KU to ITO. Rise up to University Tun Hussein on Malaysia. Okay, and then we have a branch. I think Pak Agus, my friend Pak Agus, Professor Agus, know about this in branch in Pago, where we have a diploma department there. We have Faculty of Science there, and then we have a Faculty of Technology, Engineering Technology. Okay, and then after that, in 2020, we managed to get a space in Tanjung Labo, okay, in Batu Pahat, where there is an aeronautic program. We will have an aeronautic program. We will have landing of plane. We will have a hangar there. So we will have a piloting and repairing program there. Okay. Next. Can I have mic? Okay, thank you. So it's easy for me to to show you. Okay. So this is the latest picture of UTHM. Okay, in the middle is our library, the biggest in Southeast Asia library, and it is in Parit Raja. Okay, on the right side of me, we have the Tanjung Labo, the piloting course, and then Pago branch, where there's 3 departments there. Okay, next. Okay, we have so far for academic we have 20 programs. Okay, technology and TVET, and we also very famous in TVET, technology vocational educational course. Okay, we have 84 program in TVET and technology, And management, we have 11 programs, 3 aeronautics. We have 2 actually new program in rail, and then 8 in BTech. BTech means Bachelor in Technology. Okay. For your information, in Malaysia, we have 3 types of universities. We have no the old one like UTM, like UM. There is in research universities, and then we have another. They call it Malaysian conventional universities. Okay, UITM, you know UITM, UMS, Unimes. That one is conventional. But for UTHM, we call it Malaysian universities. We have 4 universities in MTON. We call it MTON, MTUN network, Malaysian Technical University Network. We have UTHM. We have UTM Melaka. We have UMP, University Malaysia Pahang, and we have UNIMAP, University Malaysia Police. We have 4. So because of these technical universities, we have a special program, we call it BTech, a Bachelor of Technology. So we are the technical universities. So we have programs there. We have Faculty of Engineering Technologies. So this is different with other universities in Malaysia. Next. Okay, we have technical and vocational faculties. We call TVET faculties. And then we have computer science and information technologies. We have applied science and technologies. I think after this, Mr. Prof. Agus will visit applied science and technology faculties. We have engineering technology, just now I said. We have diploma studies, technology management and business. We have mechanical and manufacturing engineering, mechanical engineering. We have EE, electrical and electronics engineering, and we have civil engineering. So if you look at this slide, I think we can divide it in half. Half of it engineering and half is non-engineering. Okay. Next. Okay, in research, we have 4 under engineering. We call it Institute for Integrated Engineering. So we have 5 center for engineering. One is research. Research is soft soil. We have a research in soft soil. We have research in rail for railway train. We have MIN SRC. This is my COE, Center of Excellence, Microelectronics and Nanotechnology Samsudin Research Center. And then we have AMMC. This is Advanced Material Manufacturing Center. And then we have EM Center. This center is to provide electromagnetic compatibility research. Okay, EMC. And then for others, we have MyRevet. This is Malaysian research for TVET. Okay, we have Transform for social sciences, and then we have an Institute of Ahli Sunnah wal Jamaah. We collaborate. This institute collaborate closely with the Johor Majlis Islam Johor. So they have a good relationship with our Negeri Johor state. Okay. So this, on the right side is the center. So we have the Center of Excellence. We have a Center of Research. So Center of Research is under faculty. Center for Excellence is directly under the VC, the DVC. So we can look at this. Okay. Next. Okay, this is my faculty actually. Okay, this is a new building. I think less than 5 years. I'm for electrical and electronics. Okay, next. Okay, just now I said the Center of Excellence. Okay, I think you can skip this. Okay, from the view, okay, this is the whole picture of UTSM. I think it's not updated, but if you look at today, there is more buildings cleared in the map. Okay, so this is the quite big. I think uh, I don't know the exactly square meters, but it's quite big. I think. Eh? Right. So next, our center is located at the middle. So the chancellery is there. Sorry, my pointer is. And then we have mosque, masjid. We have convo building behind the library and the chancellery. Okay, next. So this is my collaborators or my research in Min SRC. So the flag is no shows that which country that they get their PhD. So most of our researchers in Min SRC is from Japan and Malaysia also. So we do handle our research according to Japan style. Actually, they call it COSA, something like that. So we have me as a head means head principal. We have a lab there, and then we have PhD student. Under PhD, they will guide master student. Master student will guide the bachelor student. So same in Japan, I think. Okay, so we have that structure. So we help each other. Okay, next. Okay, this is the building of Min SRC. Okay, this is the old one, not updated, but it's like this. We have collaboration around the world. We have industries come and use our machine. We have so far we have graduated I think more than 20 master PhD students, and currently I think more than 35 master students enrolled in our center. Okay, next. Okay, so we talk with my research. Okay, my expertise is to prepare nanostructured material. Okay, based on this material, we're going to use so many applications. My PhD is in solar cell, dinosaur solar cells. We try to use it in photocatalytic in wastewater treatment. We use in thermoelectric. We use it. I have student doing it in thermoelectrics. I have student, PhD student also doing mechanominism. It's not TiO2, but mainly my lab is we are doing zinc, TiO2 and zinc oxide. Currently, we have one PhD student who will try to grow zinc oxide for thermoelectric application. So this is, as you know, the TiO2. I think physics department they don't know. They should be students around here should be well known of oxide material. Okay, this is the basic of TiO2. Okay, the photocatalytic means when we something material heat illuminate with light. Okay, the electron and hole will be separated. Okay, so because of this process, it can what to it can extract the pollutant or any organic material in solution. So next. Okay, so the basic. When I did my PhD, I used TiO2. Okay, we know that TiO2 they have three phases. They have bruchite, anatase, and rutile. Usually, people are using anatase, but seldom there is a few people using rutile. So because of that, I try to improve rutile. Okay, That's why I turn it from normal particle to nanostructured material. Okay. From that, I enhance, because if you look in dye-essential cell, as for example, um, so not many people are using rutile. There is a drawback of rutile because there is a, after this I will show you the benefit of rutile compared to anatase. Okay, so uh, we try to dope, in these studies we prepared in nanomaterial, and then we dope the nanomaterial with Ag. So we enhance, when we change the nanomaterial, we enhance the surface area, and when we dope something, okay, it enhance the electron movement, so we can, because, and then these two, the two things that we have done, we improve the photokinetic towards methylene blue. So we not our target in experiment, we are using methylene blue, but our aim is for palm palm oil. Okay, so this is why we dope, so we can create a narrow band gap. Okay, of course, many people, the doping process is a very general. So, but how we going to dope in rutile phase of TiO2? Okay, usually people are using this doping in silicon and other things, but how we going to prepare this dope TiO2 using a very simple method? We call it hydrothermal method. And then why dope? So we have a electron trap. So because of due to this thing, this dope, we can has a electron trapping effect in our TiO2, and then we have, due to this trapping, we can delay our recombination of the electron in our material. So this will help to improve the photokinetic when we are using rutile phase TiO2 nanostructure. Okay, we call it flower because it's a flower-like. Okay, okay, next. So, okay, our target is for our country for POME. POME is palm oil effluents, okay, mills. So we have POME, or we can sometimes we call it POMSE. Secondary, we have POME and POMSE. So this is the byproduct from the factory of palm oil. So we're going to, there's the reason why you're preparing this is there is no post separating between catalyst and treat water. We try to improve how we going to separate, how to we avoid. Why you going to prepare a film instead of powder? Okay, if you can imagine film and powder, of course, when we talk about photocatalytic, the powder is better compared to the film because it's round. Yeah? In powder, we can have a reaction of 3D or round in the powder. But when we prepare in film, I say there is limited limitation. So how are we going to improve with this film? We don't want to use powder because if we use powder for POMSE, for example, treated water, we cannot get the powder back. It's difficult to get back the powder. Okay, the best thing is to use, we plug in the film, the catalyst, and then after that we take out. So there is no TiO2 or no byproduct or no other materials in the treated water. So we can just go through into the river. So this is the idea that we, instead of powder, we try to make it in film. But of course, the film have some limitation. So, and then the rutile phase will activated by photon in visible light. When we dope TiO2, we can decrease the band gap, and then it will react in visible region of light. Usually, photocatalytic or TiO2 there is it will be active when we have UV light. We try to narrow down because in spectrum, the percentage of visible is bigger compared to UV spectrum. So we try to get it in visible light. Okay, this is the motivation or the novelty. Okay, next. Okay, just now I said it. Okay, anesthesia, people are using, this is, I think you know already, anesthesia, we prepared 300 to 500 degrees Celsius to get the anesthesia. But in rutile, usually people have to annihilate more than 900 degrees Celsius to get rutile fish. Okay, but after this, I will show you, we prepared it 150 degrees Celsius. Okay, for anesthesia, it can change. Okay, it's not. They call it a metastable fish. It's not stable, and then less light scattering and low reflection index. Also for rutile, it's nice. Okay, it's a higher temperature, good in light scattering, good in electron transportation, and higher reflective index. So when we prepare it higher and temperature, so we have this type of light scattering. Light scattering effect means it scatter more compared to anesthesia. Okay, next. Okay, doping, the modification process of pure semiconductor oxide to create imperfection in material structure by inputting certain amount of impurity atoms is controlled manner. So doping, we introduce something to the material. Okay. So why silver? Okay, so less toxicity. I think people know about this. AG, use I think use in refrigerator to anti-toxic something, and then less cost, greater antibacterial effect. We have an antibacterial effect compared to platinum and gold. Okay, silver has in charge separation, creating by Schottky barrier between the material element and TiO2 metal element. And silver also increase TiO2 absorption of energy in the visible light. So we do, we can decrease the depth and then we can manage invisible light. Okay. All right. Next, catalyst. We have two types of catalyst. One is mobilized catalyst powder, and we have immobilized catalyst film. We don't want to prepare. Number one, we will focus on immobilized catalyst film. We want to use film. Just now I said that we just want to plug in, and take out from the water, polluted water. So this is our aim. So, okay, for mobilized catalyst, just now I said it's in powder. If you imagine in powder, okay, it has high surface area. And then we have, it's quite expensive because we have to prepare a large amount of powder, okay? And then difficult in post-separation. Post-separation means after we treated the wastewater, how are we going to collect back the powder? This is the problem that we are facing now. It's okay to produce in powder, but how we can get back? If we talk about 1 liter is okay, but about 1 pond, a big pond of POMSE, that's the problem. Okay, difficulty in recycling because of aggregation of the powder. So yes, come back to when it's powder, they have a effect of agglomeration. So it's not practical, or we have to it's the one use only. But if in a film, we can use so many times. All right, okay. Immobilized, just now I said that cause effect, okay. We just use film and then we can use and take out again, okay. Less physical impairment and better long-term of performance. Just now I said we can use it many times. Okay, next. Okay, experimental. Next, this is how we prepared. Simple. We use chemicals, and then we mix it. Okay, and then we stir and put it into autoclave, and then we put into oven, and then we get flour like AG dope flour like CO2. Okay, okay, we have a simple and low cost method. You can see there's no sophisticated machine. All right. And then decrease agglomeration between particles. Okay, can prepare highly homogeneous and crystalline. This is 150 degrees for 10 hours. Okay, next. So this is how we measured our samples. Okay, next. Okay, next. All right, next. We are using 300 watt of xenon lamp. Okay, metal blue. All right, next. So this is the XRD. Okay, you can see that in the left is the XRD. There is no silver peak. Okay, for information, this we have this peak without annealing. We don't need any annealing process. After we take out from the autoclave, we already have this peak. It's already crystalline. Usually people heat it, annealing it to get a crystalline fish, right? Okay, there is no AG, and then concentration increase because of the lattice purity and crystal symmetry. Okay, this is on the right side. Right side is Raman, agrees with the XRD. You can see Raman, there is no peak, and the peak is broadened due to the oxygen vacancies. Okay, and then below is the FRSM. Okay, next. So this is the structure of the nanoflower just said. Okay. Um, we notice that the active area of TiO2 nanoflower is the edge of the tip of the nanorods. Okay, if you look at the end of the tip of nanorods, this nanoflower is combination of nanorods. So the active of surface is only the end of the nanorods. So we have some limitation there. So that's why we try to dope it, make it lower band gap. Okay, and then with this surface area, with the dope with AG, we increase the performance of the photocatalytic. Okay, you can see that a very good shape of nanoflower. Okay, with value in lattice value of 0.2, 0.3. Okay, and next. Okay, we manage. Okay, A is undoped. Okay, B, C, D, when we dope it with 0.5, 1.0, and 2.0 weight percent. Okay, we managed to decrease the band gap. Okay, from 3.2 down to 3.0. So we managed to compress the band gap. Next. Okay, this is a PL. Okay, shows the effect of PL in our sample. Okay. Okay, next. So if you look at this, we can see that the best when we dope at 1.0 weight percent of AG, it give about I think in 70%, 75% of material blue. So after this, we're going to prepare a large scale of film, and then we're going to use it, this film, in the actual in factory, palm oil factory. Okay, next. Okay, just now I said it about this, so this is the metal blue. Okay, next. Okay, we managed to at 1.0 weight percent, we increase from about 60% with undoped, we increase to 75%, which is we have active facet at 110 and 111, and then due to the oxygen vacancy of 3+. Okay, next. Okay, this is the conclusion. Okay, next. Okay, if you want to I think it's a quite brief in my presentation. This is data from my student applied sciences, applied science, okay, journal. So if you want the journal, I can give it to you. This is all the detail of the data, how we actually discuss it in this paper. Okay, it's a Q1 paper. Okay, next. Okay, thank you very much.
Okay, thank you very much. You can go. Very interesting presentation and knowledge. Actually, I cannot stop his presentation, but time limit us. And for the second keynote speaker, I will mention her biography. Her name is Dr. Hendri Widiandari. She is famous person in UNS, very famous. Okay, she graduated from Universitas Diponegoro in 1998, and also from her master study from ITB Bandung in 2002. He got her PhD from Hiroshima University Chemical Engineering in 2008. And without any further ado, please, Dr. Henry, you can present your material in 30 minutes. And after she end her presentation, we go to Q&A session. Thank you very much, Dr. Henry. Close to here. Gerakan from Yunus.
Oke, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Yeah. Good morning, ladies and gentlemen. Honorable Professor Ahmad Yunus and Dr. Harjana and all audience. First of all, I would like to thank the Professor Budi Purnama and the committee to invite us to share our research activity in this event. Today I would like to share about the same topic with Professor Koirul about photocatalysis. And the title of the presentation today is Metal Oxide Semiconductor Photocatalyst Synthesis and Application. Okay, the presentation outline is shown in here. First, about the motivation and story, fundamental aspect of photocatalyst, photocatalyst potential application, strategies and challenge, material synthesis, and future outlook of photocatalyst nanotechnology. Next. The motivation. The world we live is composed of about 70% of water, and only 2.5% is freshwater. On the other hand, the industrial activity cause the environmental problems such as air pollution, water pollution, etc. About the water pollution, there are many ways to decompose the pollutant, such as using the activated carbon adsorption, and then by chemical UV radiation and using ozone. However, this technology sometimes produce such as byproduct and some secondary pollution. And furthermore, next. Air pollution and also climate and humidity makes the building like become dirty. because of some fungus, bacterial, on. So the advanced oxidation process or AOP by photocatalysis reaction is a promising technology. Okay. Oh, yeah, okay. Sorry. What is photocatalysis? Photocatalysis is the acceleration of a reaction by catalyst using light as a driving force. Next. Okay, next. This is the reason why we are using the photocatalysis technology. First, cheap price. Cheap price because the raw material is abundant and cheap. And second, environmental friendly because of converting the organic contaminant to CO2 and water. And third, energy saving because of working under ambient condition. Initiated with UV and visible light. So we can use the solar radiation directly in the working of the photocatalyst. And fourth, sustainable technology. Photocatalyst has an excellent catalyst stability. So this is the sustainable technology. Next. Talk about photocatalysis. Professor Fujishima of Tokyo University, Japan, accidentally discovered the photocatalyst. Professor Fujishima produced the hydrogen by water splitting and using TiO2 and water without electricity, but using irradiation of light. And in the 1972, the discovery of photocatalysis was published in the British Science journal Nature. And 1980, various effects of photocatalysis were discovered and applied to the industrial technology. 1992, the technology to apply a thin layer of TiO2 was developed in Japan. 1994, Dr. Ichinose of Saga Ceramic Research Laboratory succeeded in manufacturing water soluble titania atau TiO2. And the first patent from the Pilkington, PPG, and SSG about the self-cleaning windows. Next. Okay. Let's jump to the fundamental aspect of photocatalysis. Maybe recently Professor Koirul was delivered about this fundamental aspect, but okay, I will shortly describe this fundamental of photocatalysis. First, the absorption of light. So a suitable wavelength of photo energy. So the H nu is greater than or same with the energy gap. A second, transfer of an electron and hole to the surface of the semiconductor. Recombination of electron hole pair during the reaction process. And then stabilization of the electron hole at the surface to form the trapped electron and a hole. And next step is reduction and oxidation of the molecule at the surface. And the last process is exchange of the product at the surface with a reactant at a medium. This is the reaction of the photocatalysis. Next. The absorption of light in the back, step 1, the red highlight, and the subsequent redox reaction at the surface, step 5, the red light and the red highlight, yeah, and the K process in the photocatalysis. Meanwhile, the step 2 and or 4, sometimes occur too fast to be included in the reaction steps. And next, okay, next. And this is the, how to say, the rate of the fact. Yeah. This equation so to us about the rate of the production of electron and hole. Okay. Next. Okay. Yeah. As we said before, that the main key in the photocatalysis is redox reaction. Redox reaction, this is about the TiO2. Yeah. Next. Next.
Waalaikumsalam.
Okay. Electron and electron hole recombination is on the order of less than 30 picosecond. Hence, efficiency is low than 5%. The efficiency of the photocatalysis depend on the how well one can prevent this charge recombination. Next. This slide so to us the metal oxide semiconductor photocatalysis. So metal oxide semiconductor has to function, decompose, and detoxicity of stain, organic materials, organic molecules, bacteria, dyes, and etc. The reaction continue until the organic molecule become harmless, and the photocatalysis is almost a permanent process. The detail of the mechanism of the photocatalysis process is shown in this slide. Next. Yeah, okay. For the application, sometimes the photocatalyst is immobilized in some substrate, so coating in the substrate. When the light incident to the semiconductor, the electron is jumped to the electron in the valence band jump to the valence band and produce the electron hole pair. We call the electron hole pair. And next, yeah. Okay, this is the electron hole pair. Electron is in the upside and the hole in the bottom side. Next. Next. Yeah. This is the reduction reaction between the electron and oxygen in the air produce the anion superoxide. Next. Produce anion superoxide, and then the hole between the hole and the humidity occur the oxidation reaction and produce the hydroxyl radical. Yeah, next. Produce the hydroxyl radical. Next. Okay. Yeah. Okay, I continue. This is the hydroxyl radical. So, who is eat some bacteria, fungus, organic pollutant. Yeah, the hydroxyl radical. Yeah. So the hydroxyl radical decompose some bacteria, virus, organic pollutant, and etc. to become the harmless substance such as this one. such as water and CO2. Yes, this is the complete mechanism of photocatalysis process for organic pollutant degradation. Okay, what happened to the bacteria? Yeah, the free radical hydroxyl kill the bacteria like rubber, perampok ya. So the photocatalyst act as the rubber, which is energy deficiencies and eat the bacteria or virus. Okay, in this time, yeah, why we use metal oxide semiconductor? This is the reason, yeah. Metal oxide semiconductor are considered as a material of choice in the chemistry and material science due to their diverse application. Metal oxide have a close packed structure in which the coordination spare around material is occupied by the oxide ion. Metal oxide is extensively used in different fields of chemistry due to their easy of formation and fascinating chemical, physics, and magnetic properties. So the specific characterization of the specific characteristic of the semiconductor, metal oxide semiconductor is in the band gap energy. Yeah, like this. And what kind of the metal oxide semiconductor such as titania, zinc oxide, ferrite oxide, tungsten oxide, bismuth oxide, and etc. And the source, light source, we can use ultraviolet light and visible light. So the feature of metal oxide semiconductor photocatalyst is one, metal oxide semiconductor have a high surface area, stable morphology, high stability, reducibility, and desirable band gap. The potential application of the photocatalyst, we split in three functions. So photocatalyst first have a properties of hydrophilic surface condition, and then have the energy application, and number three about decomposition of organic substance. So there is many kind of application of the photocatalyst, not only for decomposition of the organic pollutant, but also the photocatalysis can also use as the fuel production, fuel production of CO2 reduction, water splitting to hydrogen production, and methane oxidation. And for the environmental aspect, the photocatalytic atau photocatalyst can be used as the wastewater treatment, bacteria removing, and also air purification. Okay, we skip. And however, the photocatalyst have some constraint. Yeah, have some constraint. First, fast electron hole recombination. So this is we have to prevent the electron hole recombination. And second, very low UV and visible absorption, and low catalysis stability. So what is the strategies? The strategies is one, we can use metal and non-metal doping, such as silver, platinum, and gold. And non-metal doping, we can use carbon dot atau C dot, like Professor Koirul delivered already. And two, we can use heterojunction photocatalysis, such as heterojunction like PN junction in the electronic devices. So and cerium oxide or using titanium and tungsten oxide, etc. And number 3, by generating of cation anion defect. This is the strategy to improve the quality of the photocatalysis. Okay. For example, yeah. So, what is the function of dopant, metal dopant or non-metal dopant? The function is to first to modify the energy gap, so the absorption of the light can be shifted from the UV light to the visible light. And dopant should be both good electron and hole trap. So the electron hole recombination can be prevented. So the production of the radical hydroxyl is more better. The efficiency of the photocatalysis depend on the various charge transfer event and migration of the charge to the surface. Okay, this is the role of metal in a metal titanium nanocomposite. Yeah. Okay, so same with Professor Koirul. Metal nanoparticle act as the electron sink or electron pool, so promoting interfacial charge transfer, reducing charge recombination. And this is the some research activity that do at my laboratory. This is the tungsten oxide doping with platinum produced by flame spray pyrolysis. This result is from the joint collaboration with Hiroshima University. And the PT co-catalyzed tungsten oxide was very effective to decompose the organic pollutant. The organic pollutant models, we use the amaranth, methylene blue, methylene orange, and extra. So to know how good the photocatalyst, we can see from the left side of the slide, yeah. So in 1 hour we can change the color of the methylene, the color of the amaranth from red to the clean. So this is very effective. Next is zinc oxide. Yeah, zinc oxide by flame spray pyrolysis. So we developed the flame spray pyrolysis in our laboratory. Why flame spray pyrolysis? Because using flame spray pyrolysis, this method, we can produce the fine particle, single multi-component materials, dense, hollow, porous, and nanoroot structure material, and also relatively monodisperse particle in one step process like this. Okay, this is the porous zinc oxide, and we can see here that the this material can degrade the amaranth in about less than 2 hours. Okay, next, this is the zinc oxide doped with PT by hydrothermal method. The method is same with the Professor Koiro already said, like this, very simple, but we have homework in here because the yield of the product is very small. Yeah, the yield of the product is very small. Okay, this is the SEM and XRD to prove that the material is product can prepare well. Yeah, and okay, we can see here the percent of degradation or percent of elimination in less than 2 hours, the methylene blue become or degrade, yeah, well. This is the best condition is at the temperature of 160 degrees C and no further heating after the production using hydrothermal. And okay, next, this is the same ZNO zinc oxide doped with PT by hydrothermal method. And we try to change the amount of the PT dopant. And we can see here after 3% of PT is the best condition. And on this material, it's very effective degrade the methylene blue in the visible light than the UV light. So the addition of PT is successfully improve the quality of the photocatalyst in visible light. Okay, the other method is using salt gel method. This is titania, and then this is the titania doped with silver, same problem. But not only for the methylene blue degradation, we also try to use this material to eliminate the bacteria. To eliminate the bacteria, this is the okay. We use the obstacle zone. The obstacle zone, larger the obstacle zone is better the photocatalyst. And we can see here that this material is effective to decompose the Escherichia coli. Yeah, Escherichia coli. Same, this is the titania doping with Ag by hydrothermal method for methylene blue degradation. And the material changed from white to the dark. And this is the recently result in our laboratory production of, okay, terima kasih. Zinc oxide, nitrogen carbon quantum dot by hydrothermal method. Yeah, we can see here that the nanostructure can be synthesized using this method like this. And yeah, this is the nanoflower. Yeah. Yeah, can reduce, can degrade the methylene blue in 1 hour. Like this, same. This is, we try to change the parameter in different hydrothermal time and also in the heating. But okay, this is, yeah. Not only for the methylene blue degradation, but also for the removal of bacteria, and effective in Staphylococcus and Escherichia coli. Okay, and the future outlook of photocatalyst technology. We can see here, this is not only the laboratory, activity, but also the photocatalysts have already applied in the real life, I think, yeah. Panasonic, Japan, and Soarla, Jerman, develop water purification technology to produce drinking water using photocatalyst and solar light. India, Brazil, develop textile cleaning technology using photocatalyst, TiO2, microsphere, and solar light. And then Daikin AC, ya. Daikin develops air purification technology using photocatalyst titania. And then Palcoat Soma Co. Japan developed the photocatalyst product for antifungus, antibacteria, and antiviruses. Yeah, and this is the sum of building that apply the photocatalyst in the paint, tile, aluminum walls, glass, and tin. And okay, this is the landmark building that applying the photocatalyst technology in Cowboy Stadium, USA, Kansai International Airport, Central Pompidou, France, and also in Spanyol. Okay, the last of this presentation summary. The photocatalysis is an environmental friendly and sustainable technology for water treatment application and air purification. The current and future challenge is the development of photocatalyst material that can be activated in visible light so that they can be applied outdoor using sunlight and indoors. Photocatalyst product can be implemented on an industrial scale. Okay, here I would like to thanks to my student and colleagues, my institution, Sebelas Maret University, and also my former institution, Diponegoro University, and to institution that support the research funding, Minister of Education, Culture, and Research and Technology, Minister of Agriculture, the World Academy of Science, TORE, TSF, Indonesian TORE Science Foundation. And okay, this is the message: save our planet by keep clean, keep beautiful, keep hygienical using photocatalyst. Okay, thank you very much.
Thank you very much, Dr. Henry and also Prof. Khairul. And now our session is Q&A. So I hope that there are a bunch of questions from the floor. So if you have any question, please raise your hand and mention your name and your affiliation. Okay, any question from the floor? Okay, please. So, and mention your question to whom? Committee, would you please to give him microphone?
Yes. Thank you very much. My name is Erlan from BRI, and I want to ask both Professor Herul and Mr. Henry. This is about the future prospect. I interest in catalyst, but now, as you know, the catalyst in powder is still remain in the market. So in photocatalyst, in my opinion, they depend on the light, yeah, to ignite or to activate the catalyst. Also, Professor Herul said this only one dimension, yeah. How to make this more optimum in the future? Maybe I don't know. But you use only put in doping, and this is, in my opinion, is if compared to powder, yeah, maybe only powder. We know they have maybe in porosity and can react more active, yeah. For industrial prospect, I think powder is more important there. And we know Indonesia it is for our country. Indonesia is very important, yeah, to develop the catalyst, yeah, because we need some maybe collaboration with Malaysia, yeah, because as I know, the catalysis market is depend on only maybe the like Japan or America, yeah. Now, what do you suggest for our country, especially Malaysia and Indonesia? Maybe you have a roadmap, yeah, to get a 10%, 20% in catalyst. Thank you very much.
Okay, thank you, sir. Okay, please, Prof. or Doctor, you can respond to the question.
Thank you for the question. For moving forward, just now maybe Prof. Andri, she's now preparing the powder, right? For me, just now I presented that we prepared the nano tower, and then it's in thin film. We prepared in film. So we wanted to prepare because in film, because the problem for post separation that there's now, after we treat, how we going to take back the nano catalyst, how we going to no, to get back the catalyst 100%. We don't want to that the catalyst go down to our river. So for industry, for future, I think that's why we are thinking to prepare in large scale of in film type. That's why in film we have to prepare it in a low band gap because we want the visible light, and then we have to prepare in dope. Okay, in dope, we dope it and then we improve it in visible light. For industrial, for bigger application, I think before this we going to make it in a module on in large scale instead, or maybe 1 meter times 1 meter film. So we're going to put in the pond or something, and in large pond maybe we can use it, and then after that we can easily take it out. So there is no powder, no residue left in the treated water. So that's is I think the things that we going to do for future.
Yeah, I agree with Mr. Khairul, Professor Khairul. And to improve the quality of the photocatalyst, there are many ways. First, improve the surface area, because the photocatalyst reaction is occur in the surface of the semiconductor. And the second is modification of the semiconductor, such as band gap, band gap modification, and then how to say, electron pool trapping, and so on. And for the scaling up, there are two, I think, two ways. First, immobilize on the substrate, and before that, of course, the photocatalyst must be how to say, homogeneous and stable in the some solvent like water and so on, like that. Okay, thank you.
Is there any
Mr.
feedback,
Ibrahim.
or you satisfied with the answer?
For our
Okay,
country.
for our country. What are the
For our
suggestion?
country. Suggestion.
Yes.
Yeah. The suggestion. Yeah. Okay. It is the easy question, but it is difficult to answer. Yeah. Suggestion to the country. So maybe photocatalysis is not to be focus in our country, Mr. Irfan. So it is need to hard effort, yeah, effort to close to the government, yeah. But we have like association of photocatalysts, yeah, between print and other university like UNS and ITB, ITS, and so on. Yeah, we have the Association of Photocatalysts. I don't know how to to suggestion to the to the government about it. Yeah, sorry.
Because we are government also.
Okay, for me, maybe you can plan propose a project to big large scale. For example, film. Maybe you can collaborate with my team, my student actually. She's prepared a very good screen film. Screen film, maybe we can prepare in large scale. As first, we can prepare. We combine it. We make a small scale, maybe 10 cm times cm, but we make it many pieces, and then we combine it. Okay, we combine in large 1 meter, 1 meter, and then when we can test it, we combine all the film, and then we put in that which area with any polluted river or something. Okay, that before that we must make sure it's a visible light reacted film, and then it has a low band gap, low band gap. So in my research, I think we are going towards that. Maybe after this, if we manage, my dream is to put that big film in one pond, and then after one day we take out. Hopefully, inshallah, it will be clean. This is my dream.
Okay, so the key is networking, right, and teamwork from scientists and also engineers. Okay, we still have 5 minutes because I will normalize the schedule. The beginning is dragged, and then so I have to finish this session in 10:30. So is there any other question from the floor? Okay, please. Committee? One of you can take the microphone and then give it. Okay, you can
Check.
tell your question.
Okay, introduce myself. My name is Firmansyah Nugroho. I am Sebelas Maret University undergraduate student from Department of Physics. This is my question for Dr. Khairo. Enjoy yesterday to Candi Sukuh Kemuning. Okay, I saw that in the presentation of PPT in the Dr. Khairo, I saw that related to doping. In several study, we seen that doping is done a lot of steps to improve the performance of a material. That I would like to question as the definition of the doping itself, and what are the limit related to doping? Is it limited to a certain amount of doping concentration, and what is the maximum that can be referred as that is a doping, not a new material? Thank you.
Okay, please, bro. You can answer.
You wanted to know the definition of doping?
Yes, to like limited to certain amount of the doping.
Okay.
So what is the maximum that is doping? Okay.
So actually, to answer that question, there is no maximum or minimum of doping actually. So you have to know, we have to know the what type of material that you want to dope, what is the amount. So we have to optimize. In other words, is to optimize. We have to prepare in various parameters, and then we do experiment, okay, to look at which one give the highest impact, significant. So to answer that, you have to prepare a various type of parameters. And then try to dope at a certain amount, okay, because we don't know. Each material will be different. There is no, for example, AG this amount, PT there this amount. There is no such a thing as a fixed amount of dopamine. So we have to optimize it. Okay.
Okay. I see in some paper like more of 5% the concentration of the basic material is say by say like substitution, not doping. So how about that?
Substitute doping or
Under 5%
Uh-huh.
of the concentration, they say doping, and more over 5% the concentration say substitution material. Yes. How about that?
Then is definition, I think. You said that below 5% of weight percent, right? They call it doping.
Yeah.
More than 5%, they call it substitution.
That is just like this is a new material or just doping? It's
Maybe,
like,
yes,
yeah.
okay. I don't know about the 5%, but if you add large amount,
Yeah.
that one is not a doping. Doping is a process that we spot a small amount, but it gives significant effect. Okay, the dopamine must be in small amount. Yes, but that 5% is I don't know about the person, but if you talk about doping and maybe adding or substitution, yes, large amount they call it maybe adding, or we not call it as a doping. Doping is a small amount of material. Okay.
Okay. So mainly not cannot say the maximum concentration of this doping or substitution.
Yeah. After we do the optimization, maybe you can see that the optimum amount dopamine is like this for this material. Okay, we cannot, and then we don't say that the maximum is for this, because we must find the significant result. Okay.
Okay. Thank you, Dr. Khairul.
All right.
Okay, thank you very much. I think it's depend on the scale. Maybe in our background composite, we call it additive. And I think there is no consensus about the value of a threshold for the additive. Someone told 5% or 1%, but there's no consensus about that. And I think it's only depends on the association or maybe the research field itself. Okay, thank you very much for Professor Khairul and Dr. Henry for this valuable discussion and also knowledge sharing. And I would like to close this session. Before I close, the main important for this session is we have reached very far on science, but sometimes we got a problem in how to make it in mass production. So the key words is engaging between engineer and scientists, and this is not in nature but by design. And normally in UNS is by nature, right? But the most important is by design, because for by design we can plan our target and goals such as photocatalysts, metal oxides. It's very important thing in real life. 10 years ago, I've tried to make a reactor and tried to make a nano zinc oxide. My background is product development, not material science. I just try to how to make this powder becoming mass pro and fast production. And at the day, I can produce 100 grams in 1 hour for nano zinc oxide using thermal plasma. And I think we can collaborate between scientists and engineer to make it implementable in industry. Thank you very much, and please give applause to our distinguished speaker. And thank you to close this session. From me, apologize for you all if I have any mistakes for my moderation. Thank you very much, and Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Ubaidillah, for being the moderator for the first session of the plenary lecture.
So, but before that, we will have a photo session today. I'm pleased to Professor Budi Purnama to give a merchandise here to our keynote speaker, Professor Khairul, and also Associate Professor Henry Widiandari.
Okay, ladies and gentlemen, we will now continue to the second session of the plenary lecture with our keynote speaker, Professor Muhammad Aziz and Associate Professor Mohsen Farahat.
And for the session will be led by our precious moderator, Ibu Dr. Engineering Kusumandari. And also she is graduated from the Physics undergraduate program, Universitas Sebelas Maret, and also Physics graduate program from Universitas Gajah Mada, and Crystalline Material Science and Doctoral Program, Nagoya University. And currently, she is occupied as Assistant Professor in the Physics Department and Faculty of Mathematics and Natural Sciences, Universitas Sebelas Maret. And here her research focus on material physics. And everyone please give a round of applause to Dr. Engineering Kusumandari. The time is yours.
Okay, but before that, we will have a photo session together. Please to Professor Khairul and Dr. Ubaidillah and Dr. Henry to have a photo session together with Professor Budi Purnama and Professor Agus Prianto. Also, Ibu Dr. Engineering Kusumandari. So please come on stage to have a photo session. Okay, maybe for the participant, you can rise as we have going to have a photo session together. Everyone, you can rise. Please for the committee to help to take the picture. Okay, thank you very much. We can continue to the second session of the plenary lecture.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. I am Kusumandari as moderator in this session. We have two keynote speaker in this session. The first keynote speaker is Professor Muhammad Aziz from Tokyo University of Japan. Assalamualaikum, Prof. Aziz.
Waalaikumsalam warahmatullahi wabarakatuh, Ibu.
Nice to meet you. Okay, and the second speaker is Professor Mohsen M. Farahat from Central Metallurgical Research and Development Institute, Cairo, Egypt. Assalamualaikum, Prof. Mohsen.
Waalaikumsalam warahmatullahi wabarakatuh.
Assalamualaikum, Prof. Mohsen.
وعليكم السلام ورحمة الله وبركاته.
Okay, what time is it now in Egypt?
No, I am now in Japan. I am not in Egypt.
Yes, what time is it now in Egypt?
Now in
It's
Egypt.
now in Japan.
Yeah, yeah,
Oh,
yeah.
okay. Okay, thank you.
You are
And,
welcome.
now about the first speaker, Professor Aziz. His research is about energy system, process design, power generation, carbon capture and storage, hydrogen production, renewable energy, and energy conservation. With Scopus Index of 36, he has a lot of professional experiences and publications, and you can find out more through the Scopus ID or Google Scholar, I think. And about the second speaker, I will read later. Now, allow me to welcome to the first speaker, Professor Muhammad Aziz, to deliver the presentation. Professor Muhammad Aziz, the screen is yours.
Okay, thank you very much, Bu Kusmandari. Assalamualaikum warahmatullahi wabarakatuh. A very good afternoon, hopefully, or a very good morning for all of you. Selamat pagi untuk semuanya. It is actually my great pleasure to be invited today. I'm Aziz from Tokyo University. And first of all, I just would like to appreciate and also deliver my honor to all of the committee, especially to my guru, Prof. Budi Purnama, and also to all of the participants today, and also actually to my seniors, Professor Mohsen. Thank you very much. It is a really good time to see you. I think we have not been met, but I think it's 15 years. So it is really good times to be able to meet you again here. So before I'm starting my thoughts, I just would like to start sharing my presentation first. Okay, so hopefully that you can check my presentation slide over there. So first of all, because my background is basically mechanical engineering, and also what I'm doing now is currently correlated with any kind of energy systems. So we are developing any kind of hardware and also software technologies correlated any energy systems, any energy conversion technologies, or etc. So today the talk will be quite more general, but hopefully that it is still correlated to all of you, because I believe that energy is all very broad things, broad topics that can be done by all of us actually. So not should be limited to mechanical engineers or any kind of science or mathematics people or others, but hopefully that it can be done for us multidisciplinary matters. So today's talk will be entitled Delivering Net Zero Society Through Optimum Utilization of Carbon-Free Energy Resources and also Digital Twin Technology. So hopefully that today I just would like to talk about the digital twin technology, and we are adopting this kind of technology today because we would like to match also our simulation technology and also the technology that we have in actual monitoring systems and also etc. So before I'm getting into my core of the talk today, I just would like to introduce our lab. So we call it as the Energy and Process Integration Laboratory, and it has been set in 2019. So it is basically quite young laboratory in Tokyo University. So now currently we have about 12 students. And we have also about 8 visiting internship students and other 2 researchers. So in total, we have about 12 people working together in our laboratory. So basically, we are actually welcoming for all of us, for all of you to join us and also to have collaboration with us. So it is our great pleasures and also honor in case that we can welcome and also have these discussions and also collaboration with all of you. And some topics are also available in our website. So I think you can check further the detailed information about our website in epi.is.u-tokyo.ac.jp. So, and also this is the little brief descriptions of our university, that now Tokyo University as the first university in Japan, but now unfortunately it is ranked 23rd in QS, and also this year I'm really shocked that in Times Higher Education's our ranking drops to 29th. So we dropped from 34th last year, and this year we must be patient in 39th. And it is the first Imperial University, and I think the biggest university in Japan. And things, yeah, in general, I think they are not so really big. And the total students that we have is about 27,000 students. I think that's also quite familiar also in recent university. Some in recent universities, I think, have a bigger scale of students number. And also we have now currently 16 Nobel laureates correlated at the university, whether there are faculties or alumni of our university. And regarding our institute, I belong to Institute of Industrial Science, which is the second engineering of Tokyo University, and we have 5 different departments, and I belong to mechanical and power functional systems. So we are basically working on any mechanical correlated technologies, but basically Institute of Industrial Science is really not so pure mechanical engineering or any kind of department engineering such as in Hongo campus. We are basically much more multidisciplinary. So although we are doing any kind of mechanical engineering, but basically in our research also, we are facilitating, we are also blending with other disciplines, including chemical engineering, also electrical engineering, and also etc. So things, yeah, there are some policies in our university that I think it is really better to share to all of you, but in brief. So in our university, we don't have any accreditations. So we don't pursue any kind of accreditations, whether in Japanese accreditations or in any international accreditations. And also the basic idea for us is that we are nurturing the researchers, especially the young researchers. And also we have also developed any kind of dynamic classes, and we have also now adopting quarter systems rather than the semester systems. So basically all our classes are divided to quarter systems. So it is about 3 months. Yeah, basically net 2 months. So basically why we adopt this kind of quarter system is because we believe that this kind of quarter system is much more beneficial, whether for students and also for faculty. Whether for the students, I think we thought that the students can be more focused for their credits, for their classes, and also for the faculties. What we got is that it is easier for us to schedule our own schedule. So sometimes we can focus on delivering the classes for 1 quarters, but also we have quite independent times for maybe in case that we would like to focus on research or for having any kind of visitings or etc. We can also spend another quarter for doing that. And also we have now currently also adopt the open university bonds. So in our, we are still in the trial mode that we would like to consider that the research is also economically benefit. So we are developing several investments and also several research facilities based on this kind of university bonds. And this bonds is also quite soft, quite long soft. So it is about 40 years loan, but it is really, really competitive. And as the information is that when we open this kind of university bonds at times for the first times, and then the bonds itself has been sold less than 1 day. So I think many stakeholders, especially the companies or etc., they are really eager to buy any kind of this kind of university bonds itself. And for today's talk, my talk will focus on the energy aspects and also especially on the energy sustainability. So usually I started with this kind of slides, and as we could see over years that when we are talking about the energy sustainability, basically we are talking about 3 different pillars, including the energy security, energy equity, and also finally the environmental sustainability. Let me start from the energy security. Energy security means not only correlated with any kind of quantity aspects of the energy itself. So sometimes in conventional manner, we just define the energy security correlated with our capacity or capability to cover the demands of the energy itself. But actually, what we are now dealing with is that we are more dealing with any kind of quality aspect of the energy, because when we are dealing with the energy means that in real-time manner, simultaneously, we must be able to cover high quality of the energy itself. So not only delivering the energy from the supply to the demand side, but the important thing is that how we can guarantee high quality of the energy, so the balanced energy in simultaneous manner. So the second aspect is correlated with the energy equity. So for the energy equity, basically we are dealing with any kind of opportunity to all of the stakeholders. So we are not against dealing with the conventional definitions of the energy market. In this case, now currently all of the stakeholders, whether in conventional market maybe can be defined as the customer, but now currently we are defining all of the stakeholders as the prosumers, as the producers and also consumers. They can behave in real-time manners. So all of us can also purchase and also can sell the energy that we can generate. And also in when we are dealing with any kind of renewable energy, means that usually renewable energy is widely and also thinly distributed. So it means that when we would like to optimize the resources of the renewable energy available in the country or the regions, means that we must optimally facilitate all the stakeholders to deliver, to produce and also deliver the energy that can be harvested. And the third aspect is correlated with environmental sustainability. And in this case, I believe that all of you understood about this one. But I just would like to emphasize that the environmental sustainability is not only correlated with the CO2 generations or any kind of emissions, but also we must keep in our mind the importance of the balance between the air, the soil, the water, food security, or etc. So it means that we are talking about the integral lives of the environment itself. So among this kind of 3 energy pillars, we have also strong correlation with the Sustainable Development Goals. Among them are strongly correlated, but also among them are also correlated. And for the energy transitions, now currently some countries are pursuing for creating or achieving zero neutrality in 2060, 2050. Yeah. We are not discussing further whether this kind of zero our carbon neutrality is really achievable or not. Some people maybe we don't believe that maybe in 2050 Japan can reach the carbon neutrality, or Indonesia in 2060. But the most important thing is that we can set any kind of roadmap that can finally, although it cannot realize completely, but minimally it shows our motivations, it shows our commitments to create any kind of the reductions in CO2, in any kind of emissions, and also finally also create any kind of zero carbon neutrality. So in energy transitions, basically we have 4 different aspects: decarbonization in the electrifications, and also decarbonization in non-electrification. So it is including also the transportation. So now currently, I think many transportation sectors have been shifted. So from any kind of fossil fuel base to any kind of more cleaner based transportation systems, including the train, including the buses, including also passenger cars. And also now currently I think some aircraft companies, including Airbus, Boeing, etc., they are also developing hydrogen-based airplanes. So the third aspect is correlated with energy productivity. It is also correlated with energy conservations. But basically, there is a little bit difference between the energy productivity and energy conservation. Energy conservation usually talks more about our motivations, our intention, strong will to reduce the energy consumption itself. But for the energy productivity, it more focuses on any kind of our technological capability to reduce the energy consumptions while we are maintaining the productivity of activity that we have. And also finally, also in case that we don't have any kind of capability or any kind of technology to create this kind of decarbonizations and also for energy productivity or energy efficiency, finally, we must have any capability to set up any kind of scenario that can produce the minimum carbon budget constraints. And I think this is also the shift in the transformation of the energy systems. But I don't want to go deeper in this case. But what I just would like to mention for you is that the trends will be really different. So currently we are laying or depending ourselves strongly on any kind of fossil fuel-based baseload generation, including the coal, including the others. But in the futures, I think because this kind of generation side also will be generations technologies will be phased out and also phased down in the futures. Finally, we will try to facilitate maximally the renewable energy. But unfortunately, the renewable energy basically is fluctuating. So some people now, I think some people are, what we are facing now currently, especially like what really happens in the Germany currently, is that some renewable energy, although they have been constructed well, finally they are curtailed. So some wind turbines in the northern Germany, in the northern part of Japan, like in Hokkaido Islands, basically they are not operating anymore. What will happen over there, because there's any kind of limitations in the grid to deliver the energy harvested or generated from the wind turbine itself. So we must have any kind of capacity to balance, to deliver, and also to balance the fluctuating energy or fluctuating electricity generated from renewable energy. And that's why we need any kind of adjustings, and also finally also any kind of energy buffer that can cover this kind of fluctuations. Otherwise, the number of the curtailment of the renewable energy will be really huge, and that means also the loss in terms of the economy and also in the terms of the technology. And this is the concerns and the energy transitions. There are some, including the environment, economy, and also the socials. Now we are in the transitions period for reaching any kind of carbon neutrality, but it is really not easy, because what really happens over here is that some people have vested interest also. They have settled down their business based on the conventional energy systems, but in case that they would like to move on to any kind of new energy systems, means that they must take any kind of new opportunity for them. So this is not really easy. And also for the social, we are also facing any kind of some challenges related with the jobs creations or etc. So I think how far we can guarantee, how far we can tackle down this kind of problems is also very important. And for the future energy options, and also we are not only talking about zero carbon neutrality in 2060 or 2050 according to the country, but the more important thing is that how far we can plan, we can figure out ourselves beyond the carbon neutrality itself. So we cannot think that now renewable energy, maybe we are thinking that renewable energy is the solutions. But basically, when we are trying now to massively adopt renewable energy, means at that times we are starting another problems. We can see what really happens currently is that when the renewable energy, especially the wind energy is the wind turbine is massively constructed, and there is any possibility in some areas that the wind speed drops down. So what's really happens over that, there will be any kind of temperature rise in certain area. So that's also another problem. Also, in case that we install massively like solar panels in certain areas, it means that there will be any kind of environmental changes over there. So while we are thinking that renewable energy, yeah, it gives maybe some solutions, but the problem is that how actually we can optimize further about these things. Sorry, I have a call, so I must see after the. Sorry, I have a meeting now currently. Sorry. Okay, thank you. And then it's also what is important things. The second aspect is correlated with any kind of carbon-free secondary energy resources. So we are not only dealing with any primary energy resources, but also the important thing is that how far we can change, we can convert the primary energy resources to non-carbon based secondary energy resources, including electricity, including the hydrogen-based fuels, including the ammonia, including metal fuels, heat, or etc. And finally, also, when we are talking about the CO2, finally we come to the conclusions that finally we must be able to control the CO2 generations, to be positive, to be negative, to be zero. So now, yeah, basically in total, it's negative. It is positive. It is positive. So it just means that we generate CO2, but also we must have any capability, sometimes to be zero, sometimes to be negative. So. And so some policies, some technologies need to be developed in this case. So this is the idea for the Society 5.0 and SDGs, but I don't want to talk in detail about this one. I think I just will have to skip it because of the limited times. The today talk mainly correlated with any kind of digital twin technologies. I think when we are talking about the digital twin, some people, the definition is still quite broad. Some people they are defining the digital twin technology as the coherence or as the synchronizations between the virtual world and also with the real world. And I think that's also true. But in this case, I just would like to mention in details that when we are dealing with any kind of digital twin technology, we are not only talking about our capability to do any kind of simulations technology or to do any kind of big data technology, artificial intelligence technology, but also finally how far we can communicate well with the reality. So that's also the things that's really important. And some people now also correlate with the digital twin, with any kind of digital transformations. But I just would like to remind all of us that this kind of digital transformation or any kind of transformation that we have, green transformation, company transformation, university transformations, basically they are only a tool. They are not the main goals or the main target of us. So we have some technologies, including the IoT, to sensor for the monitoring, to sensorings, or to develop any kind of big data, something like that, to inquire the data, to collect the data, or etc. And also we have artificial intelligence to process the data. Finally, the data can give us any output that is really important for us. And also robotic and also ledger technology, including the blockchains or etc. But these kind of technologies are basically not the purpose or not the aims that we are targeting for, but they are basically the tools. So digital transformation is only the tool. What our target is that how far we can strengthen our cultures and also our capacity. So this thing is also very important. We are not we are not sacrificing our culture and our capacity for creating the digital transformations, but digital transformations is basically the basic tool. This is just a tool for strengthening our cultures, for also how far we can increase our quality of life and also our capacity itself, our imaginations, our creativity, or etc. So this is the correlation between the energy transition and also circular economy that we have. And basically, circular economy also talks about how far we can reduce the energy input, the waste, or the material inputs, and also the materials or the waste output, and also optimize the economic value and also the value that we can get from this kind of activities inside the circle. But yeah, there is some correlation, strong correlation with any kind of sustainable developments. But basically, SDGs or sustainable development goals is that basically have what more broader impacts compared with the circular economy. But for the circular economy, it just more focus on the economic aspects and also environmental aspect. And the more important thing is that we are now in the transitions period for the energy systems, but this is very, very important for us that we must adopt any kind of adaptive energy transitions. So the adaptive scenario, which is really possible for each countries, for each regions to develop, I think that's very, very important, but very crucial. So the main key word over here is that it must be progressive and also dynamic transitions. So when we set up any kind of our commitments to reach any kind of carbon neutrality in 2060, 2050, something like that, and we translate it to any kind of roadmap, how far we have any kind of feasible, measurable, and also achievable roadmap for all of us. Not only, oh, we have this kind of target, and finally we must set up any kind of very, very ambitious roadmap. And finally, this kind of roadmap cannot be achieved at all. So I think we must be progressive. Yeah, that's very important. We must be dynamic, yes. And also finally, the most important thing is that we must be adaptive with that. So adaptive means that we must have any kind of mutual communications between what we should be, what should we have in the futures, and also our capacity, our conditions currently. So for example is that in the energy systems also we need not only talk about the technology or about the communications or about the policy that we can have, but the most important thing is that however we as the main player in the system itself must have any kind of commitments and also capability also to shift or change our consumption's behavior. And this kind of adaptive behavior is very important. We are not against the kings as in the energy market itself, and we must be served by any other stakeholders. No, so we must have a responsibility in ourselves that we must have we must feel that we must actually realize that we are a part of the systems, and we must we have responsibility to participate in it. So how we can change, how we can behave adaptively with the conditions, what really happens currently in the simultaneous manner, that's very important. And this is also innovative and sustainable energy industries, but I think all of you are also quite familiar with that. Now, currently also in our laboratory, we are developing any kind of big data technology for this one. We are dealing with any kind of, in case that we would like to develop the energy scenario for setting up or maybe constructing a new model for the energy system based on hydrogens or etc. Basically, finally, also we are dealing with any kind of big data. So historical big data, weather data, and also consumptions data. And finally, that's very important. And based on this, how far we can ensure ourselves that this kind of big data can be handled well, and we can get any kind of the true data. So the problems with the big data are, I think it is not all, but I think we are facing with the volume, we are facing the vast velocity, and also the parity, which is very tremendous, and also finally also with the veracity. And when you're talking about the digital twin technology, as I mentioned previously also, that I think this is also the integrated energy, including the big data and also any cloud computing, simulations technology, extended reality, artificial intelligence, and also finally IoT monitorings. So you can figure out about like 2 different systems like here, that finally we must have any kind of monitoring or IoT technology that can simultaneously read up the data that was really happened in the real systems. And also we are playing with any kind of big data, historical data, and also the current data. And also finally, we must have also the simulation technology or cloud computing, artificial intelligence technology that can process the data as soon as possible. The problem is that when we are doing any kind of simulation, sometimes the simulation itself takes time, although we are using the supercomputers. In our study also, because we are developing the combustion technology for the hydrogens, sometimes the combustion simulation itself takes about 2 or 3 weeks, although we are using any kind of supercomputer with that. But how far we can tackle down this kind of simulations or prediction technology to be much more shorter, like 2 or 3 seconds, because finally, when we would like to match or synchronize together with the IoT, the big data from the system itself, finally, we need very, very huge, very fast computing technology or prediction technology. So finally, we also combine with the artificial intelligence, with the neural network to speed up our simulations predictions. And also we have finally also some other technologies to support that. And finally, what is the main target for the digital twin technology is that we would like to create any kind of accurate predictions, optimal solution decision, minimum cost, and also maximum benefits to all of us. And also these are examples in artificial intelligence in the energy systems. Now also we are developing this kind of systems. The system that can, there are some levels of the artificial intelligence, including also the classifications or etc., and also including also the reinforced deep learning or etc. But it really depends on the aims or the objectives that we would like to have. But currently also we are developing not only the prediction systems but also the optimization technology for our energy systems. So this is also the digital twin in energy systems. So as I mentioned also previously, how far we have any kind of IoT technology to simultaneously read the data of the real time of the real systems in real-time manners. And also finally, also on the other hand, we must have also the capability to do any kind of simulation predictions or etc. And finally, we can combine them together simultaneously. So this is also the application of digital twins in the energy systems, in some power generations, and also in some more broader energy systems, including the renewable energy. As we could see also that renewable energy is basically difficult to predict. And there are some fluctuations, but in case that we can have any kind of big data for about 10 years, 20 years in the last part of the historical data, and also we combine also with the weather data currently collected in some data source. Finally, also we can have any kind of accurate predictions for this kind of renewable energy systems. And also the problematic thing is that when we are dealing with any kind of customer data, consumption data, sometimes this kind of consumption data, although basically annually or monthly in average monthly, maybe it is quite constant, but unfortunately, in case that we just frame up to about 2 or 1 hours or maybe half an hour, something like that, there will be any kind of huge fluctuations of that. So this is also digital transformation in the energy sector, but I just would like to skip it. This is the smart electricity grid, but I think because I'm running out of times. So we are also now currently doing the research also related with hydrogen productions, hydrogen transportations, storage, and also utilizations. And correlated with these ones also, the main idea is that not only utilizing the hydrogen for the power generation, because in case that we just would like to use the hydrogens to generate the energy or generate the electricity, and we just would like to provide the quantity of the energy, means that the hydrogen itself cannot enjoy very good economic performance. So we must position the hydrogens to have or to enjoy any kind of prime any prime benefits in this case. So prime services, including the regulation services, including also the balancing services, or etc. So it means that the price of the electricity or the price of the energy that can be delivered by hydrogen is quite high. So not only the basic price of the energy itself. So I think in Indonesia, I think that's also still quite challenging because we don't have any open market that can support that. So the most important things before we are able to do any kind of prime or to offer any kind of prime services to hydrogens or any kind of electric vehicles or batteries or etc. We must renovate our market, our energy market first. So basically, we must have any kind of market that can facilitate this kind of services. So this is the cost of the hydrogens, but in general, I think although the cost of the hydrogens now currently is really competitive, it's also still very expensive compared to conventional hydrogens, because conventional hydrogen's price is only about $1.5 per kilogram hydrogens. That is in case that hydrogen is produced from natural gas. But for the renewable energy based hydrogens, the price is still about 2.5 or higher than that. So it means that we still have huge gap between the conventional, also the new or renewable energy based hydrogens. So some policies, including the carbon tax or etc. things, and also at the other hand, when we can optimize the technology for the hydrogen productions, we can increase the cost for the conventional hydrogens, while we are decreasing the cost for the new and also renewable based hydrogen itself. So this is the possible Indonesian energy roadmap, including the hydrogen itself. So I think this kind of roadmap is quite promising in case that we are having commitments to reach zero carbons or carbon neutrality in 2060. So we must have also commitments for us that we need also to start hydrogen adoptions in 2030 for large scale adoptions, including the co-firing technology and also co-blending with the existing diesel engine or etc. And the crucial period, I think, is between the 2030 and the 2050, because we must develop also the infrastructures for that. And when we are defining or we are constructing the infrastructures, means that at that time maybe we cannot get any kind of economic benefits of that. So when we are targeting for the economic benefits, means that we must have very good hydrogen's community, hydrogen economy, which can be reached or achieved in 2045 or after 2050. And this is a possible roadmap for hydrogens. So I think the case or the scenario will be really different with Japan, with Germany, with the United States. So in our country, I think we can focus more on the export orientation first, and also for the domestic large scale. Domestic large scale includes also the co-firing technology, ammonia to the existing coal-fired power plants, and also maybe blendings of the hydrogens with to the existing diesel engines. And finally, once the infrastructure has been set up, and also our familiarity with the hydrogen itself increased, so it means that after that we can adopt any kind of large scale or maybe massive domestic adoptions in our country. And this is the digital twin in combustion technology that we are now also developing in our laboratory. So as I mentioned previously, that combustion or simulation sometimes needs a time, 2 or 3 weeks, although we are using the supercomputers. And unfortunately, in case that we just adopt this kind of technology for predictions, means that we need really huge time for that. So we are also integrating with any kind of physics informed neural networks to to communicate with the database. So from the simulation, we get the database based on the simulation, database based on also the experimentations, and also finally also the physics and also chemical informations. So finally, we create any kind of pins, physics informed neural network, and using this kind of pins, maybe we can have more faster prediction. So in our experience, we can shorter the simulation itself for about 2 or 3 weeks. We can use this kind of pin technology. Finally, we can have predictions in about 2 or 3 seconds. And finally, also with IoT technology, we can also blends together or makes synchronously together with the real systems over years. So finally, what really happens over here is that we would just like to have any kind of, in case that sometimes happen in the real plant systems, and based on the monitoring systems, we can have any kind of real-time data based like the pressure, temperatures, or maybe any kind of chemical species or etc. And finally, we can feed back to the system, and the systems finally can predict what really happens now currently in the system itself. So that's what we call as the digital twin technology in our combustion system. So this is the real or the detailed system that we are developing currently, and some also some studies correlated with that, and our systems fortunately what we got is that very good accuracy, very high accuracy between the experimental and also with our simulations or predictions. And finally, we believe that this kind of prediction systems can be used in our digital twin technology for combustions in the futures. And also the simulations times, in case that we can have any kind of dynamic load balancing systems, we can reduce about 80% reduction. So as I mentioned previously, in the conventional calculations methodology using the supercomputers, we can take about 2 or 3 weeks. But for having any kind of dynamic load balancing technology applied, finally, we can reduce to about several days. Thank you very much for your attentions today. And in case that you have any interest, any kind of questions, it is our pleasure to welcome all of your questions. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much. Thank you very much, Professor Ade, for your interesting presentation about energy system. It's very wider from social aspect and science aspect, I think. But please postpone your question. We will move to the second speaker. Associate Professor Mohsin Farahat. He is currently an associate professor in Mineral Processing and Agglomeration Department at Central Metallurgical Research and Development Institute in Cairo, Egypt. And he got PhD in mineral processing from Kyushu University, Japan. And his research focused on physical separation technologies, surface modification, and microbe or mineral interaction. With Scopus Index of 11, he has a lot of professional experiences and publication, and you can find out more through his Scopus ID or Google Scholar. Now allow me to welcome to the second speaker, Professor Mohsin Farahat. The screen is yours.
Thank you very much. I'd like to, first of all, Assalamu alaikum wa rahmatullahi wa barakatuh. It's my pleasure to see Dr. Aziz again here. And I would like to special thanks to Dr. Podi Burnama for giving me this opportunity to meet all of you. Okay, I would like to start my today presentation. May I ask the host to enable share screen, please? Sorry. Can you see my presentation?
Any problem? Professor?
I couldn't share my screen.
But not see it here, no.
Can you enable this option?
You already share screen?
Now, can you see my presentation?
Not yet.
So but, the share screen option is not activated yet. It's not activated. Could you please activate it?
You already become co-host now.
Now, can you see my presentation?
Not yet.
Because I couldn't share my screen. The share screen option is not activated yet.
Have you clicked share screen?
I already clicked, but it is not active.
Did you open your Zoom?
Yeah, of course.
Application? And
Yeah.
then click share screen in the bottom of Zoom.
Wait a minute, please.
You can click share screen in the bottom of your screen. Yes, this one.
This is share. Okay.
Please
All
click.
participants. Okay. Okay, now.
Not yet. We cannot see your screen.
You can start. I already started. I already
But
activated.
you can send your presentation to us.
How? How can I send it?
To share screen. By a message in the
Okay. Just wait a minute.
of Zoom.
Okay.
Professor Mohsen?
Yeah.
So, to interrupt you, I think you are co-host now, so I think you must be able to share the screen actually.
Yeah, but the share screen option is not activated. Yeah.
Really?
Yeah.
But you are co-host now, huh?
I am really surprised. I don't know why. Okay, I will send now. Okay. Okay.
Is it any problem?
I already sent the file to you. Have you received?
By chat room in Zoom?
Yeah.
The computer not receive your message.
Okay. Something wrong. Haven't you received? It was sent already. I don't know.
Or you can send to my email.
Just send me your email, please.
Okay, I will.
I'm sorry for this.
Okay, in the chat box, you can see the email. ICSAS @mail.SAD.
Wait a minute, please.
Can you see the message?
Not yet. I couldn't see it. Where?
Okay, so please send
I'm
your
sorry for
presentation to this email.
Oh, wait a minute. I receive your message. So can I upload to this? Oh, okay. I will see now.
ICSAS
Okay.
at
Okay.
mail
Okay, I will send you now.
at AC@ad.
I will send you now. Wait a minute.
Okay.
I sent you.
Have you sent it?
Yeah.
Okay.
Oh, okay. Just a minute. I think I can share. Is it okay now?
Yes, very good, brother. It works well.
Sorry for that.
Access to share screen. Okay,
Is it-
please. Please write so your screen.
Yeah, wait a minute.
Okay, thank you.
Also, I'm sorry for that. Okay, I would like to thank again the organizers and all participants. First of all, the title of my presentation is Surface Modification of Minerals to Enhance Their Selective Separation. Yeah, this is me, Mohsen Farhat. I am from Central Metallurgical Research and Development Institute, Cairo, Egypt. Before I go into my presentation topic, I would like to just give a brief introduction about my research center. My research center was established in 1970. It was a branch in our National Research Center. And then with the support of UNIDO, receiving different pilot plants and facilities, the current building, the current building was established in 1980. It is in south in Cairo, in Helwan, where there are many industrial, because it's industrial area, and our research is the topic of our research institute is about metallurgical. So we have steel making industry and the coke factory and cement factories in this area. So this our research institute, although it was established maybe recently about 20 or 30 years ago, we have a lot of collaboration with different countries, and our research institute rank is one of the top in research institution in Egypt, and we have more than 500 industrial projects with private sector and international entities, including Japan, United States, and Europe. So this is a main construction of our research center. We have 4 research institutes. First one, which I belong to, is mineral technology. Under each institute, we have 4 departments, and in Mineral Technology Institute, we have mineral characterization and mineral beneficiation and agglomeration. And I'm proud to belong to this department. And then after the structure follow the flow of industrial process. So this is mineral characterization, which focus on exploration and evaluation of the minerals. And then it's our department research topic, which is to upgrading and the removal of the associated impurities with the target minerals. And after upgrading process, the step is for chemical and electrometallurgical department, extraction department, using either chemical or electrochemical method, or using pyrometallurgical techniques, which is high temperature extraction metallurgy. And another institute is Metals Technology. Under this Metal Technology Institute, there are 4 departments: steel technology, non-ferrous metallurgy, plastic deformation, and corrosion control and surface protection. And we had brainstorming in 2005. After this brainstorming, a new department was established, which is Advanced Materials, and this Advanced Material Institute. We have 4 departments: composite material, electronic and magnetic material, ceramics and refractory material, and nanomaterials. And the 4th institute we have is Manufacturing Technology Institute. Under this institute, we have 4 departments: casting technology, joint technology, and powder technology. And this is AutoCAD and the rapid prototyping manufacturing department. And this is a technical unit, which advanced analysis center. We have chemical testing, physical and mechanical and techno-economic study for pre-feasibility studies for the project, because most of our projects are relevant to industry, so we care about its economic and environmental impacts. So I will talk a bit about the facilities we have at our department. As I mentioned before, our department is mineral processing department. So we start from comminution, which means the crushing and the grinding, and the measuring is the power consumption or during crushing and the grindability. Because as you may know, to achieve a successful mineral separation, we have to first achieve liberation of the mineral from its associated gang. So we have different primary and secondary crushers and planetary different ball mills, and rod mill and ball mill and rod mill. And we have this cyclosizer. It's a type of size analysis to determine the size, the product size distribution of the material we have used. And the second, also we have unit operation, different unit operations, magnetic separation, different dry and wet dry magnetic separation, high intensity. This is based on rare earths, and this is wet high intensity magnetic separator. So we can be used in industrial, in lab. This is pilot scale equipment. And for the gravity separation, we have conventional apparatus like shaking table or jig, and the recently advanced super gravity concentrator, which is used mainly for for gold and the heavy minerals recovery. And for the advanced analysis, we have zeta potential, particle size distribution, and atomic absorption for routine chemical analysis, and total organic carbon to follow up the absorption of surfactant we use during the absorption for flotation or flocculation process. this contact angle to measure the wettability, and so on. So this is the main research interest of my department. Mineral comminution, the target is to minimize energy consumption during crushing and grinding process. Upgrading of fine-grained, low-grade ores, because as you may know, because of the depletion of high-grade ores, it became mandatory to exploit and to look for new technologies to upgrade fine-grained and low-grade minerals. We use, as you know, minerals is not like material. It's completely different. We deal with huge amount, million of tons. So when we are talking about the mineral separation or mineral upgrading, we cannot use chemical method because it will economically unfeasible. So mineral separation, it depends on physical separation techniques. Physical separation techniques like flotation, magnet separation, and next slide I will show the basics of this unit operation. These are the outline of my presentation. Just a little short introduction and what is surface modification method, and we have different methods, and we'll talk in detail about each method. Okay, so it's introduction. As I mentioned before, separation of minerals from their gangue is based on the difference in physicochemical properties. So this is flotation is one of the most common techniques that is currently used to upgrade millions of tons of minerals all over the world. So simply, flotation depends on the distinction between wettability of the minerals and its gangue. So if the mineral is hydrophobic, it means that if the mineral is hydrophobic, so it will attach to air bubble, and while the bubble are rising up, so it will carry up the mineral at the surface, and because of the pressure difference, the bubble will burst, and we can collect the hydrophobic material, while the hydrophilic one will be left behind in the solution. So, and if there is distinction between mineral and its gangue in their magnetic separation, simply like silica and the magnetite or hematite, it can be this unit operation is proper for this system. We can use it as a magnetic material, will attach to the magnet and separate it as a magnetic fraction, while the non-magnetic will stay away from the magnet and collect it as non-magnetic. It can be used for different systems. And another unit operation is gravity separation, which is based on the density. If there is a large difference in density between the minerals and its associated gangue, this technique is proper. For example, this has been used for coal, because especially for to desulfurization of coal. If we can, because of the environmental regulation, it is not allowed to use high sulfur coal because of the acid bind drainage problem. So we use this system to separate. This is very old method. This is JEG. It's called JEG. So the heavy material will be settled down, and while the light one will go up and go with the water stream in this direction. So we can separate pyrite, which is a main source of inorganic sulfur in coal. And the another technology depends on the conductivity, because minerals have different conductivity. So it can be separated according to their different surface charge. We can use electrostatic separator or triboelectrostatic separator. But in some cases, the main problem is that we cannot find differences in the physico-chemical or in the physical or chemical properties of the mineral between the mineral and its gangue. For example, molybdenite and chalcopyrite, or even not only molybdenite, chalcopyrite, but arsenopyrite, energite, tennantite, which is the arsenic-bearing mineral. And the chalcopyrite is the main source of copper. So this is the most valuable mineral, chalcopyrite. Sometimes it is, not sometimes, always it is associated with arsenic-bearing minerals like energite, tennantite. So it's difficult to separate them directly without treatment because they have similar, they are, in terms of magnetism, they are similar. They are paramagnetic or non-magnetic. And in terms of density, almost same. So we cannot choose we can't use gravity separation. And for charge, almost same, or zeta potential. So it's difficult to apply the physical separation technology directly to separate this system. Also, hematite and pyrolusite, both of them are same in terms of wettability, hydrophilic, and they have the same magnetism, and the density is same, so we cannot use gravity separation, and they carry the similar charge. Apatite and dolomite, apatite, which is the main source of phosphorus, it can be used for the production of fertilizers, and the presence of dolomites makes it difficult to use technically and economically to use ore directly in the manufacturing of phosphoric acid. So this is we have to do some surface modification techniques. We have to use this modification technique can be chemical or physical or biological or mechanical. In terms of chemical, we can use some inorganic salt, for example, like sphalerite. The chemical can act as activator. Activator means increase the absorption capacity of the surfactant or the collector to the mineral and increase its high floatability. It can be collected as floatable. So copper sulfate, if we use with sphalerite, it covers the surface of sphalerite with cobric sulfide, which has high affinity to be absorbed by some collector like PAX, potassium amyl xanthate. And the chemical not only activator in terms of flotation, but also as depressant. Sodium cyanide, but this cyanide is a little bit toxic to environment. So recently we used another reagent. This is to depress the chalcopyrite and decrease selectivity, so we can separate it from some system. Mechanism of some chemical modifiers, for example, if we use polymer like starch, it can be directly attachment because of physical absorption. So just covering the surface of mineral. So this means we inhibit the absorption of the other reagent to the surface. So we can selectively make selective absorption and the consequent selective separation. Or sometimes the chemical can react directly with the collector like this. This is its collector, which head and tail. This part is hydrophilic and this part is hydrophobic. So this means this surface now is highly floatable, which means if it is in solution, suspended in solution, and then it comes along with air bubble, so it will attach to the air bubble and float. But if we add excess of sodium hydrogen sulfide or sodium bisulfide, so this excess of this will it affects on the surface properties of sorry, and desorption the collector and decrease the floatability. So chemical modifiers can be either pH modifiers, also, or salts, or acid and polymers. For example, this is pH modifier. Because the pH modifier, as I mentioned before, the surface, the unit operation depends on the physical-chemical properties of the mineral. So, and the chemistry of solution will be effective. So, for example, if we use, if at high pH, the surface of pyrite, its This flotation recovery decreased dramatically by increasing the pH because of the formation of ferric hydroxide on the surface of pyrite, which inhibited the absorption of the collector on the surface of pyrite. And this research was done by our team here in Kyushu University. So we could selectively separate energite from chalcopyrite. Energite is arsenic-bearing mineral, which it's a big problem. So, and chalcopyrite is the main copper, as I mentioned before. But both of them, if we look at this condition, both are similar. Flotation recovery is almost same. If we add sodium sulfide, so there will be selective depression for chalcopyrite comparing to that of energite. So we can selectively float or separate energite from chalcopyrite. Another method is called carrier microencapsulation techniques that can be used to enhance the mineral separation. This technique has been used to separate pyrite from coal using flotation. We can use gravity separation techniques, supergravity concentrator, to separate pyrite from coal because of the big difference in the density of pyrite comparing to that of coal. Or if we'd like to use flotation experiment to separate pyrite from coal, we can also use these techniques, because using this technique, we can, using silica catechol, just a layer of by adsorption, and after just this selective coating, there is kind of reaction. What happens is the formation of layer of silicon oxide on the surface of pyrite, converting it to be hydrophilic instead of hydrophobic. So it is easily possible to separate coal because coal is hydrophobic. So we can, by using the carrier microencapsulation technique, it is possible to separate coal from pyrite by flotation. Desulfurization of coal. This is the result we got. This is before treatment without microencapsulation. 60% of coal was recovered. Of pyrite was collected with 90% of coal. But when we use microencapsulation, almost 90% of coal was recovered, while the recovery or the yield of pyrite was about 20% or less than 20%. The other physical, what I mentioned before was chemical method. But now we will move to physical treatment. Physical treatment includes heating, conventional heating, dielectric heating, and ultrasonic or electrostatic or triboelectric separation. By heating, conventional heating, the surface of the mineral surface charge can be changed. Not only surface charge, but also the magnetism can be changed, like what's called magnetic roasting or magnetizing roasting, or can sometimes change the wettability and the change in the mechanical properties. Changing the mechanical properties this can enhance the grindability, which in turn will decrease the energy consumption during crushing or grinding. So this is some example. This is magnetizing roasting. It was used before. It was used to reduce. So hematite was reduced to magnetite. As I mentioned earlier, the difficulty to separate hematite from pyrolusite because of the great similarity. So using hydrogen and at high temperature, about 800, was possible to selectively reduce hematite to magnetite. Magnetite is a ferromagnetic, while pyrolusite is paramagnetic. So if we use low intensity magnetic separation, it was possible to separate both. But this research we have done recently, and it is not yet published yet, magnetic recovery of hematite and pyrolusite. So we could selectively modify the surface of hematite at low temperature at about 400 degrees to increase its magnetic susceptibility dramatically while keeping the magnetic susceptibility of pyrolusite unchanged. And this was, as you can see here, how is the magnetic recovery for hematite under different magnetic separation intensity. So as you can see here, this is for hematite, the red one, for the fresh hematite, almost less than 10% at 0.2 Tesla magnetic intensity. But if we, with the treatment, the magnetic recovery increased to about 50%, and at 0.4 Tesla to almost 70%, and at 0.8 Tesla to 90%. If we look at for pyrolusite, it was, so we can separate in this region at 0.4 Tesla. Less than 10% of pyrolusite can be collected, while as a magnetic fraction, while 70% was collected for hematite. And this is the results we got for the separation of pyrolusite from hematite. And this is the we got three fraction: non-magnetic fraction, which is mainly pyrolusite. As you can see, the grade was 54%, and the iron content is 3.9%. We started with 50% to 50%. The feed was like 50% manganese and 50% iron, but we got this three fraction, which is completely with completely different chemical composition. As we can see, the pyrolusite or manganese was collected in non-magnetic fraction about 54.5%, and the weight percent of this fraction was about 54%. And if we look at the strong magnetic fraction, the grade was about the 31%, and it was mainly hematite. So we got grade iron grade was 64.8%. This grade is very high and with high recovery, and this is fraction is considered as meddling, which can be reused again, like in scavenging or in cleaning process to increase our the recovery of pyrolusite and the hematite. So selective. So this is the effect of heat treatment on the absorption of some minerals. This is chalcopyrite and the galena. As you can see, at the temperature, at low temperature, the absorption density is almost same. But if the temperature was, if the minerals were heated to about 80 degrees before absorption, so it was possible to increase the absorption on chalcopyrite comparing to galena. So increasing the absorption means we can easily separate the two minerals from one another. The next technique is the microwave treatment heating. As you know, microwave is consists of electromagnetic and the magnetic waves. With the high oscillation of microwaves, the mineral depends on its chemical composition and physical properties. There will be a response. So, for example, the mineral will oscillate in response to microwave. It is, if it is polar, like water molecules, which is used during heating process, so which is making raising up the temperature. So this is some mineral sample. This is how the minerals are classified according to their response to microwave. There is some material absorbing, which absorbs the heat, and the absorption will cause some surface changes or mechanical, leading to cracking and enhancing the grindability and degree of liberation. Some transparent, and some material like glass or silica. That's why if you add if you put if you put like glass dish in microwave, it will not be heated, and reflective like other metals. Because I think time is very, so I will go. This is the table show us how the materials have different, how the minerals have different response to microwave. So some materials hyperactive, its temperature the temperature increases to about 1000, while other is inactive, its temperature is very low. So if we compare microwave to with conventional heating, there is one advantage of microwave, which is called selective heating. By this selective heating, because of the mineral, for example, if the mineral and its gang have different dielectric constant, they will be like selective heating. This selective heating will make like stress on the boundaries of the mineral and its surrounding impurities, which will increase its grindability and increase what's called the liberation. As we can see here.
Excuse me, Professor Mohsin, your time remain 2 minutes again.
What? 2 minutes?
2 minutes again.
Okay. So, okay, that's all. I will just pass this and okay, this biosurface modification, no need to go through this. So the last thing I would like to talk about is the dry coating techniques. We can use this technique to combine the properties of different minerals and to maximize its potential. As was mentioned early in the first session or the first lecture about the comparing it to the material. I would like to compare natural mineral, which can be used as adsorbent material to remove pollutants from water. We have used some physical like this. It was removal of hexavalent chromium. We could prepare magnetic composite that is composed of natural mineral serpentine and the magnetite, and the presence of magnetite make it easy to separate it after the treatment. And another example, I just go, this paper has been published in Cleaner Production. We prepared the composite that composed from iron ore and serpentine and bentonite, and we could use to separate different mineral with high removal efficiency. We could remove cadmium and lead and arsenic and cyanide. The last mineral I will go through this one, which we could use magnetic material. This was published in scientific report recently, last month, and this one we could prepare high magnetic, super magnetic, super hydrophobic material using the dry method only, and this could be used to for the treatment of oily water separation. And this, as we can see, this is the water before treatment, is after treatment, and this video shows that sorry, the video doesn't work. Okay, so anyway, this video show us how we could use this composite to remove. This is the water before treatment, after treatment, and after treatment we use this adsorbent, and we could recover the absorbed oil by rotary evaporation system, and for multi-reuse, and it was used for different cycles, about 10 cycles. Because of the limited time, this is general conclusion, which shows us the importance of surface modification to enhance the mineral separation or to maximize the potential of our natural resources. I hope that you could get my point, and I am sure that Indonesia is rich in natural resources, and I hope in the future we can have like mutual collaboration, inshallah. That's all. Thank you very much.
Okay, thank you very much, Professor Mohsin,
Inshallah.
for your interesting presentation. Now, the session for QA. Any question or comment? Oh, please. Please mention your name and for who your question.
Okay, first of all, my name is Yoga Pranata and I'm undergraduate physics student of Physics Department Universitas Sebelas Maret. And I want to say thank you for the both of professors, Professor Muhammad Aziz and Professor Mohsin Farahat, for this excellent and insightful conference. My questions is maybe to Professor Muhammad Aziz, right? About digital twin research, right? So as we know that in this recently, I mean like in this previous year, the digital twin research is conduct in many technology startup or the engineering and also the industrial, right? So the main questions from me is like, is digital twins a concept that only targets to engineering application innovations with existing technology? I mean like, is there any impact from these digital twins, such as like maybe in the in other field like the academic or for the lecture applications or something like different or the except from the engineering application like that. Thank you.
Okay, thank you very much. Okay, Professor Aziz, please. Professor Aziz, can you hear me? Okay, please, one question more. Any question? Not yet. Okay, there is a question in the chat room from Professor Budi Purnama to Professor Aziz. Please explain grid electrical technology and possibility apply in our country, Indonesia. Professor Aziz, have you in Zoom? Okay, maybe any other activity with Professor Aziz or he can hear me. Okay, I have one question for Professor Mohsin. So you work with natural resource, is it right?
Yes, that's right. Yes.
Yes. So what's the difficult with the natural resource? For example, in the term of cost, is it cheaper or not with another?
Yeah. Yeah. Thank you very much for this question. Of course, if we compare natural resources with like new material, but composite or nanomaterial, it's very cheap and with high scalability, because we, for example, for direct use, as I mentioned, in like environmental issues like water treatment, the method we used, it's dry technology, so we can produce huge amount of this composite within like few hours, and we don't use water at all, and we just, when it is environmentally friendly, because it was separated from the environment. So if you compare this method and the material with natural mineral with new material, there is a big difference between both.
Okay, thank you. So it's cheaper.
Of course, cheaper. Yes, very cheap.
And this is one question more from Professor Budi Purnama in the chat room. Please explain the simple methods to separate hematite with other impurity in the nature or mineral.
Yeah, okay. Thank you very much, Dr. Budi, for this question. So, in general, the method we use to separate specific mineral from its impurities is based on the nature of the impurities. For example, if we are if you want to separate hematite from silica, you can use either flotation or magnetic separation because of the difference in the magnetic properties between the minerals and the gangue. But in some cases, like as I mentioned, if your mine contains hematite and the manganese oxide, it's difficult to separate directly hematite from pyrolusite without any treatment. So in this case, we cannot use directly magnetic separation. We can't use because we have to make some treatment to create like to increase the gap between hematite and the pyrolusite. So it depends on the nature of impurities you have.
Okay, thank you. Any feedback from Professor Budi Purnama? Enough. Okay. Alhamdulillah. Professor Aziz already come back in Zoom. There are two questions for Professor Aziz. The first question is from our student, Mr. Joga. The question is about the impact of twin energy to other field except engineering. For example, for academic and so on. Is it right, Mr. Joga? Or you will repeat your question?
Okay. Thank you. I will repeat my questions. Yeah. Is digital twins concept that only target engineering application innovations, or there are many impact that using this digital twin trend research, right? Thank you.
Okay, please, Professor Aziz.
Okay, thank you very much, Mas Yoga, for very good questions, actually. So regarding the digital twin technology, basically this kind of technology is broadly acceptable and also maybe also applicable in several fields. So it is not only belongs to any kind of mechanical engineering or any kind of engineering itself, but I believe that once we deal with this kind of digital twin technology, I think it is really applicable in various fields, also including mathematics and also including science or etc. So in case that, like for the material engineering, you can imagine that how now currently when we develop the new materials or we would like to find new materials, I think some people are now working on how they can develop, they can find new materials that can be maybe combined together among several available materials. So in case that we would like to develop any kind of composite or etc. Finally, we can have any kind of big data technology, and finally also the artificial intelligence to match best the materials, the characteristics of the metals that we would like to have, actually. So also in our other studies, also we have also developed this kind of digital twin technology. We are targeting for certain functions. Yeah, whether it is economic functions, maybe it is any kind of technological functions, maybe material functions, strengths, or etc. Any kind of characteristics that we are targeting for. But now maybe we don't have any established methods for that. So basically, based on the database that we have hugely in our database systems, maybe we can also have or purchase the database from outside. And finally, the main important thing is that how we can define the target functions that we are targeting for. So in case that we are able to do that, I think this kind of artificial intelligence and also digital twin technology matchings between the reality that we are facing and also the virtual reality or any kind of database systems of real simulation or etc. Maybe we can combine it together. So I think this kind of technology is not only for technology, it's not only for engineering field, but I believe that in several fields, including chemicals, physics, and also materials or etc., biology or etc. I think this kind of digital twin technology is valid and also I think can be applied well. I believe that. Thank you very much.
Okay, thank you, Professor Aziz. Any feedback from you?
Professor Aris, the questions works on me. Thank you.
Okay, thank you.
Thank you very much.
And one more, Professor Aziz. This is from Professor Budi Purnama. Please explain grid electrical technology and possibility apply in our country, Indonesia.
Okay, thank you very much, my guru. So I think this question is also very important. And when we are talking about the grid in our country, whether it is in Java and also other islands, I think we are facing several problems. So the answer is that how we can update or upgrade our grid system that can facilitate not only the renewable energy resources, but also the characteristics of the future grid systems. So it is also including the upper market that must be also applied in our futures. So, but I think we must be really wise in this case. Otherwise, we just spend our investments, huge investments to upgrade our grid, but unfortunately, we cannot get any optimum result from that. So you can imagine it's like when United Kingdoms would like to upgrade their grid systems. Finally, they found that in case that they would like to upgrade their grid systems, it is really better to them not only installing any kind of energy buffer, but the things. But finally, they found that it is really better to them to facilitate any kind of vehicle to grid technology for the systems. So again, in our systems, grid upgrade doesn't mean that we must spend a huge investment for that. No. So we must really be able to figure out what is really happens in the demand side and also in the supply side, and also during the transmission, also distributions. So like in case that our characteristics of distribution and also transmissions, that most of the electricity is generated in the eastern part of Java, while the demands of the electricity is basically focused on the western part of the Java, means that we need to have any kind of huge capability or high capability to deliver or to transmit the energy from eastern to western of Java Islands. So, in this case, we are figuring out what really happens in case that there is any kind of accident, there is any kind of emergency conditions, or there is any kind of congestions minimally. Congestions in the grids in case that finally the grid cannot deliver further the capacity from the eastern to the western part of the Java, means that finally the electricity itself cannot be covered well. So when we are facing this kind of problems, yeah, maybe we can install new grid systems, or maybe we can have any kind of additional grid, or maybe a higher, huge or more bigger grid for that. But unfortunately, the investment will be really high. And so sometimes we can also solve this kind of problem softly. So maybe we can adopt any kind of other systems, including also the vehicle to grid, and also maybe energy buffer, which can maybe I think facilitate some new stakeholders or new business in some areas, like in the western part of the Java. Maybe we can have any kind of additional services, or maybe ancillary services, or maybe new business to invite the new stakeholders in case that there is any kind of fault or any kind of in case that the electricity cannot be delivered well from the eastern to the western part of the Indonesian or Java Island, means that maybe some new stakeholders or some new business, they can deliver this kind of ancillary services. So ancillary services that can support the grid. So at that time, maybe they can deliver the energy or the electricity and or etc. So it doesn't mean that all the upgrades of the transmission distribution systems or grid system itself must be followed by huge investment. No. So yes, we need the upgrade itself, but we can upgrade systematically, we can upgrade softly, and also, yes, physically also, that's also important. But the important thing is that's not the physical thing, is not all the things. So we must have any capability to figure out what is the limitations, what is the challenges, what is the reality that we are facing is now currently. So how we can get any kind of appropriate answer and appropriate solutions to the real condition itself. So some technologies, so I think now like PLNs now is developing energy buffer based on the pump hydro or etc. That's a good move, but we can imagine that building this kind of energy storage is very, very expensive. While I'm not sure whether this kind of energy buffer can actually answer the problems of our energy quality or not. So I think when we can figure out what will happen in the futures, like the demands for the chargings of the electric vehicles, the demand for the new or maybe the fluctuation in the renewable energy or etc. in the futures, things finally we can have the correct or appropriate answer or solutions for that. Actually, thank you very much for that.
Okay, thank you very much, Professor Aziz. Any feedback from? Okay, okay. This is a very interesting and valuable discussion, but we are sorry the time is limited. So thank you very much, Professor Aziz and Professor Mohsen, for your valuable and interesting presentation. Please give applause for the speakers. Thank you very much. And also for the participant for the active participation. Thank you very much. I apologize if I, as moderator, have a mistake in this session. So again, I would thanks to Professor Aziz and Professor Mohsen. We hope Professor Aziz and Professor Mohsen in the future can come to Universitas Sebelas Maret. Okay, thank you very much, and wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much for Dr. Engineering Kusumandari for being as a moderator today for the second session of the plenary lecture.
Okay. Thank you very much for our keynote speaker, third keynote speaker, Professor Muhammad Aziz. And here is the certificate from the ICSAS 2022. Please everyone give round of applause to Professor Muhammad Aziz. Thank you very much, Prof.
Also, then for the second here is the certificate for Associate Professor Mohsen Farahat. Please everyone give round of applause for Associate Professor Mohsen Farahat. So ladies and gentlemen, so we are in the end of the plenary lecture today, and the next schedule will be a prayer break and following by the parallel sessions.
But before that, I would like to remind you about the parallel session. The parallel session will be started at 1 p.m. and the closing ceremony will be held in each parallel room.
And once again, everyone here, to give a big round of applause to our wonderful speakers today.
On behalf of the organizing committee, we are saying thank you for your stay here to join this conference. It was really an honor to serve you all, and
see you at the International Conference on Science and Applied Science 2023. Wassalamualaikum warahmatullahi wabarakatuh.
mau foto. Ayo kita foto yuk. Tolong ya. Biar asli. Mundur dong, 2022 dong. Kamu kanan dong.